everybody, this is Rudra Pradhan here and welcome you all to BMD lecture series, and today we will continue the inferential analytics and that to part 2, and we are on the process of discussing multiple sample case. In the last couple of lectures we have discussed various cases by using T statistics, Z statistics and F statistics. Again we will discuss the same problems by using F statistics and that too in multiple variate means multiple sample case. So, typically it is a multivariate case. So, when we have actually one sample, then the problem is a very simple one, then little bit complex you may have a problem with the two samples, and then again the complexity will start when we have a more samples simultaneously. So, that means the moment we will move from univariate to multivariate, then the complexity will start increasing. So, as a result, so the test structure will be slightly simple to complex. So, what we will do here? So, we like to take a particular business problem, and we will see when there are multiple sample case, what are the process through which you have to what are the process through which you have to check the kind of difference. So, now if it is actually one sample case, so we are checking that whether sample mean is having difference with the population mean, and when there are two sample case, then the mean of the two samples, the difference of two mean samples is converging towards population mean difference and something like that. So, now when we have a multiple sample case, so typically let us say there are 4 variables, and for that means typically 4 sample case, and then we have a different kind of observations, and then in the multiple sample case, one of the typical inference which you like to have or you like to observe is corresponding to this problem and sample of observations. So, we like to check whether there is a significant difference within the samples and between the samples. So, again we will go for some kind of variance check, and that the consistency measure, and here the F statistic is to check whether the difference between the the variance between the samples and within the samples are significantly different as different to population kind of variance. So, here the idea is to check the mean difference between within the group and between the group. So, what are the process through which you have to investigate? Let us see the case of the structure called as ANOVA, right. So, these are the learning objectives which you are having, and the idea the highlights of this lecture is to typically go for analysis of variance, then that too we like to know the theoretical aspects or computation of ANOVA, that is the analysis of variance, and then ANOVA tables and examples. Of course, we have already discussed the concept of ANOVA tables with the examples, but here the process is a little bit complex, and that too with multiple sample case. Then scope of ANOVA, and the extended version of ANOVA, that to models, factors and designs, then 2A analysis of variance, and then finally block designs. And so, the learning idea behind this particular structure is we like to know what is the explanations behind the purpose of ANOVA, and describes the model and computations behind ANOVA, explain the test statistic of ANOVA, and will connect with the one way ANOVA, two way ANOVA, then three way ANOVA, and that is the concept called as ANOVA. So, that is why what I have mentioned earlier. So, it is the degree of complexity. So, typically if you go by F statistic only, so then the complexity will start with one way ANOVA, two way ANOVA, three way ANOVA, then the concept called as ANOVA, that is called as a multivariate analysis of variance. So, now so in the one way ANOVA case, with respect to a particular attribute we will check the difference, and in the case of two way ANOVA we may have two different layers through which you check the difference, and in the case of ANOVA you have multiple layers through which you have to check the difference. So, let us see first the structure with respect to one way ANOVA, And before we start the process of one-way ANOVA, let me highlight what is exactly the ANOVA concept. And of course, we have already highlighted little bit about this concept in the last lecture. So, ANOVA, that is analysis of variance, is a statistical method for determining the existence of differences among several population means. So, that means here actually we have a multiple samples and each sample is drawing from different populations. So, that is why we have a different population means, and we have also different samples and we will draw different samples, and then we will check different sample variance with population variance. That is the idea behind this particular structure, what we call as ANOVA. And ANOVA is designed to detect the difference among means from population subject to different treatments, and it is a joint test. The quality of several population means is tested simultaneously, or we can say that jointly. ANOVA test for the equality of several population means by looking at the two estimators of the population variance, and hence it is the kind of analysis of variance. Typically, it is a variance statistics, and any particular any particular situation or any particular case test or t test, the calculated value may be negatively skewed, may be positively skewed, but in this case it will be it is always actually positive valued or positively skewed. In an analysis of variance, we have r independent random samples and each one corresponding to a population subject to a different treatment, and ultimately the total sample size will be n1 plus n2 plus n3 up to nth observation. So, that is what the total populations. Then the samples which we are drawing are samples which we are drawing from the population n, that is x1, x2, x3, and then sample variance corresponding to x1, x2, x3 are s1 square, s2 square, s3 square and s1 square. So, these are the background about this ANOVA. So, that means actually we have a multiple populations case and we are drawing individual samples from these populations, and then we are checking the mean of these samples or variance of these samples are statistically different from each others, whether there is a difference or there is no difference. So, depending upon the kind of inference, we will take some kind of management decisions. So, that is how we are here to test the particular structure. So, hypothesis test for ANOVA having some kind of assumptions. So, we assume that independent random sampling from each of the earth populations, and we again assume that the earth population under the umbrella of they are normally distributed and with means mu I that may or may not be equal, and then with equal variance. So, that means typically we have R populations and we are drawing samples, and that then mean of the samples we are assuming that mean of the samples are equal, but we are checking the kind of difference with respect to equal variance, that is actually sigma square I, right. So, with this particular conditions, the hypothesis testings for this ANOVA is like this. So, we are testing that whether the sample means are different to each others. Since we have a multiple samples, so here the idea is actually corresponding to multiple samples and they are drawn from the different populations. So, their population means are equal, that is the hypothesis we have to build, and corresponding to this hypothesis, null hypothesis, the alternative hypothesis that they are not equal. So, that means mu I equal to mu I equal to mu 1, mu 2, mu 3 like this, or mu I not equal to for all I starting from 1 to rth row or rth number of series. So, that means typically in simple language, so all the means are equal, population means are equals and population means are not equal. This is the simple way you can elaborate, and then you draw the samples and check whether there is a significant difference between the two. So, here F statistic follows the ratio between estimate of variance based on means of means from the earth samples and divided by estimate of variance based on all sample observations. So, that is how the game between the kind of upper part and the lower part. So, we are checking the kind of difference, and that is the significance difference between these two groups, And then since we have already discussed the ANOVA concept in the last lecture, for f criticals we need 2 degree of freedoms, and in this particular case, so here first degree of freedom will be r minus 1 and n minus r. So so it's question actually the typical ANOVA structure will be like this. So this is the series, and here let us say I series and J series. So we like to check whether so these are the points, So we like to check whether there is a difference between within the group and between the group. So now, so these two difference should not be statistically significant, and whether they should not be significant or not, then depending upon samples or the kind of problem, so we have to check. So if there is a significant difference between these two, so your the kind of decision, the kind of strategy will be different, but we need to know the kind of inference, and on the basis of this inference we have to take a decisions what should be the next step behind the particular on the basis of this particular problems. Okay. So now typically the one way ANOVA structure is like this, which we have already highlighted. So all the population means are equal, and at least one of them different from others, right. Maybe actually suppose there are for populations mu1, mu2, mu3, mu4, at least between two pairs are not actually equal. That is the conditions for alternative hypothesis, and the testing procedure follows the F statistics, and it is the ratio between these two mean squared statistics, and F the kind of outcome or the kind of inference typically depends upon the comparison between F critical and F calculated. So typically we will calculate F like this, and then I will discuss details about this particular structuring in the next slide. So in the meantime, so this is F calculated, and the decision rule will be when F calculated will be overtaking the F criticals depending upon the alpha, then df1 and df2, and then if not, then we cannot reject the hypothesis. If the F calculated will overtake the F critical, then we have to reject the null hypothesis. That means in this case, so your null hypothesis mu1, mu2, mu2 are not actually equals. So that is what the inference or the kind of conclusion which you draw on the basis of this particular testings. Let us see how is this particular testing. So here actually in the entire analysis of this particular ANOVA, so the typical structure will be, so okay, so let me give a sample problem first, then I will come back again here. So the typical examples will be like this, and here you see here, so this is actually one sample, this is a second sample, then third sample and fourth samples. So now not necessarily that they have a uniform observation, they may have a different observations, and the idea behind this null hypothesis that it is done from the population 1, population 2, population 3, population 4, and then the typical null hypothesis that mu1 not equal to mu2, not equal to mu3, not equal to mu4, and at least one pair should not be actually equal. That is how the testing is all about. So we are in the process of we have a total samples by clubbing all these things. So as a result, so there are 3 typical variants you will find in this particular process, that is what the ANOVA all about. So that is called as total sum of squares by using all the samples, and we are checking the that is actually it is nothing but actually the difference between the square of the difference between the sample point, individual sample point with the combined mean. So that is what the total variance that we call as total variance, which should be equal to the variance within the group and variance between the groups. So that is the typical and the kind of F is nothing but actually the mean square within the group, the ratio between mean square within group and the mean square between the group, and followed by the corresponding degree of freedom. So let's first discuss the particular concept, and then we will come back to this particular problems. So accordingly, so the typical structure will be like this. So we can okay. So this is how the particular structures what we have already discussed, and there are all 3 variances. So this is actually sum square total, that is total variance within the particular combined samples, including all individuals. That means n1, n2, n3. So for instance, corresponding to that previous problem, so we have a 4 samples. So the total samples will be n1 plus n2 plus n3 plus n4, and then sum of all the items divided by the corresponding sample points will give you the mean. That's called as combined mean. And the variance, the individual means with the individual individual value of x corresponding to combined mean, and then squaring. If you add up for all the samples, then the particular variance is called as sum SST, that is the total sum of square or sum square total, and then it will be equal to exactly error sum of squares, that then between sum of squares. So, that means within the difference and between the difference. So, that is typically represented by SSC and SSE. So, mean SC and mean SC is nothing but actually SSC divided by the corresponding degree of freedoms or and the corresponding degree of freedom, and accordingly you will calculate the F statistics. And in the SSC, it is nothing but actually this is the mean of a particular samples, and this is the combined means, and this is the sample adjustment. Okay. So, then in the case of between sum of square, so it is the sample of a particular variables, and then the mean of that particular variables. So, in any particular point of time, you need to calculate only 2 items, and in fact actually SST equal to SSC and plus SSE. This is always true for any problem or any contest. So, as a result, if you like to report manually, then at a particular point of time at least 2 you can report, then by default third one can be obtained. So, for instance, SSC, if you need SSC, then you need to calculate SST first and then SSE. So, by default you can difference between the 2 you can get SSC, or if you directly connect with the software by default will give you the values of all these items, that is SST, SSC and SSC. So, SSC plus SSC will give you the weight of SST. So, accordingly, so these are the following descriptions. C is the number of treatment labels. So, that is actually column, means it is typically the structure is the column wise variations and row wise variations. So, this is the arrangement, and sometimes the problem can be analyzed with the balanced samples, and sometimes the problem can be analyzed with unbalanced samples. Not necessarily the sample size will be uniform in all the cases, like the component which you have discussed earlier, like correlation coefficient. In this case, there is the difference of sample size may not affect, but ultimately we need to know what is the significant difference between within the variance and the between the variance. Okay. So, now corresponding to this, so let us check what is the exactly concept. So, what we have already discussed. So, SST equal to SSC plus SSC, that is nothing but total sum of square equal to treatment sum of squares and error sum of squares. So, this is a different kind of concept, but it is the typical actually structure is the total variance is nothing but actually within variance and between variance. So, this is the other way you can represent the particular variance. So, total variance sum of squares total means it is a total variance for the combined samples. Then you like to check actually within variance for individual samples, then between variance for each case or each kind of row. So, as a result you will get the concept called as sum square totals. So, corresponding to this particular structure, so the the ANOVA table will be like this. So, first you calculate the sum SSC, and then the kind of SSE, and then finally SST. So, either you can individually calculate, and again for for simplicity you can calculate any 2, and the third one can be obtained by default, and the adjustment factor will be here. So, MSC is nothing but SSC by the kind of difference, and okay. So, this is what actually. So, this is the SSC by degree of freedom, and this is the SSC by degree of freedom, this means sum squares, and f is nothing but actually. So, it is the SSC by degree of freedoms, and then SSC by degree of freedom. So, this is nothing but actually called as MSC, and this is nothing but called as MSC, and this is what actually the concept called as f calculated. And then with the help of samples, so you can get the f value. Then on the basis of f value, so we have actually degree of freedom 1 and degree of freedom 2, that is actually sample adjustment row wise and column wise. Then finally you have to check what is the f criticals, and the final check will be, or the decision making or the decision will be the comparison between f calculated versus f critical at a particular probability levels. That depends upon the alpha which you have to fix or you have to focus, and accordingly. So, the typical structure will be like this. Let us take with discuss with a kind of examples. So, the same example which I have highlighted here, and in this case, so we have actually 4 samples, and this is the sample 1, sample 2, sample 3, sample 4, and these are sample descriptions, and this is the total of all these samples, and by default mean of the sample will be 31.59 divided by 5, similarly 50 by 22 divided by 8, 45.42 by 7, and so on like this. So, accordingly mean is calculated, and you can find out the variance also within this particular, but here actually variance should not be 0 in any point of time. If variance is 0 for any particular sample, then this particular sample should not be included in the particular process of investigation. So, now having this kind of this is kind of descriptive statistics, then we will go to the ANOVA structure and check whether there is a significant difference within the group and between the groups. Okay. So, corresponding to this, the particular structure will be like this. Okay. So, first with the help of this particular formula, and you can calculate the SSC, and you can also calculate the SSE, and once you get the SSC and SSE. So, by default sum of these two will be equal to called as SST, that is the total sum of squares. So, now so this is not actually difficult to report if you have a small kind of if sample size sample numbers are small, and then the sample observations are some small, and in fact if you have actually Excel spreadsheet or any kind of statistical software, then just easily actually enter the data, and you can have all these ANOVA items, right. So, these are all actually first and ANOVA item, that is SST, SSC and SSE. So, once you get SST, SSC and SSE, then with the help of degree of freedom, so you will find MSC and MSE. So, now the ratio between the two with degree of freedom. So, we will get the kind of f statistics, and then that f statistic will compare with the critical value, and accordingly we can get the inference, and we will go for some kind of typical management decisions to need to be taken for this problem. And in this case, so this is how SST, either you can calculate or you just add up it. So, in order to know the details, let us come here, and this is what actually SSC which you have already calculated from these samples 2, 3, 6, 5, 8, and this is 1 for 9, 2, and this is actually SST is 39150, but SST we have no business, but our business is with respect to MSC and MSE. So, that is nothing but SSC and SSE. So, with respect to degree of freedom, so you have to calculate. So, typically SST degree of freedom is n minus 1, and then the MSC degree of freedom is nothing but actually C minus 1, that is actually column representations, and then n minus C, that is total samples minus columns, will give you the degree of freedom for the other part, that is the MSE part. So, that is in this particular case, so this is for SST, this is for SSE, and this is for SSC. So, then accordingly the degree of freedom will be 3 for MSC, and then for MSC it is actually 20, and then for SST, so it is actually 23. So, accordingly So, you can actually calculate it, and then the 10.18, this is how the f calculated value. Then you go to the f critical, and this is what actually f calculated, and then you can go to the f criticals, and then you have to take the decisions. So, now corresponding to this problem. So, this is what exactly the ANOVA tables. So, this is the between difference, this is the between difference, and this is the kind of within difference, and these two will give you the kind of total, and that is what SST is all about. So, now this is mean, and divide by degree of freedom you will get this, divide by degree of freedom you will get this ones, and this divided by this divided by this degree of freedom will get this ones. Okay. So, now the ratio between the two will give you f statistic, that is f calculated. Now, so to get to know the inference about this particular calculated, which is on the basis of sample information, and then fixing alpha, and we have already degree of freedom on the basis of samples, and we like to know what is the critical value. So, the critical value for this particular structure is like this here. So, fixing alpha equal to 0.05 and your degree of freedom 320. So, that means 320 you go this way and this way, then you will find here the kind of critical value. So, now on the basis of your f calculated and f criticals, so you have to take the decision whether you have to accept the null hypothesis and whether to reject the null hypothesis. That means the idea is whether the population means are equal or population means are different to each others, right. So, in this context, so this is what actually f criticals. So, now in the next slides, so the typical inference will be 3.10 is the kind of range which you need to take a decisions whether your calculated value is overtaking 3.10 or accept under the 3 critical value. So, that means typically the whether you are on the basis of sample informations, whether your critical value is overtaking the calculated value overtaking the critical value or under the critical value. So, then accordingly you have to. So, that means typically, so this is actually critical value. So, this is what I have calculated. So, if it will be crossing this critical value, so then you are rejecting true null hypothesis. If not, then you have to accept the true null hypothesis. So, in this case actually f calculated is coming 10.18, and then f critical is already given 3.10. Since f 10.18 actually overtaking 3.10, so that means we are here actually. So, that means we are rejecting the true null hypothesis, and then the inference or the kind of conclusion is that mu 1, mu 2, mu 3, mu 4 are not same, they are different, and since they are different, so that means there is a significant difference among the sample means. So, now this will give you more interesting that which two pairs are actually problematic. So, and for that we may go for pairwise comparisons. So, now in this particular situations, the conclusion is that there is a significant difference between the within the sample and between the samples, and accordingly, so here we are rejecting the true null hypothesis, and then the conclusion is that the means of all these population are not same, they are actually different. Okay. All right. So, this is what another way you can highlight this particular problem, and the typical if you this is one way ANOVA, and this is what actually the kind of sample statistics and the corresponding ANOVA here, right. So, sample statistic followed by mean of all these samples 1, 2, 3, 4, and corresponding variance. So, the variance itself showing that it is not a problem, and it is under controls, because if lower the variance, then it will be more consistent of this particular series. Higher the variance is a problematic, and again if it is 0, then still it is a problematic, and since variance are not actually equal and not high, so the problem is actually under controls, and we are in a position to check now whether there is a significant difference between their the variance between the group and within the group. So, in this case, So, it is coming actually 10.18 and that is crossing actually F criticals at the probability level of 5%, and then the conclusion is that the sample means are not actually same, they are different. So, which sample is having a high difference or low difference, that will take care by pairwise mean comparison again, and for that we have a different approach or again, and let us see how is this particular structure altogether. In the case of multiple comparison test, so once ANOVA will give you some kind of significant result, then that means it will give you another kind of route where we like to know which two pairs are actually problematic. If they are not statistical, if F is not showing statistically significant, then you may stop, but if it is coming significant, so that means one particular samples may be problematic. Since here there are 4 sample case, so the pairwise comparison case will be 4C2 times, right. So, these are the, so that means typically 4 into 3 by 2 into 1. So, that means technically 6 different cases you can find out, and then you check what is the which two pairs are significantly different, right. So, that means actually like x1, x2, x1, x3, x1, x4, x1 okay, x1 x4 with 4 samples, x1, x2, x1, x3, x1, x4, then x2, x3, then x2, x4, then finally x3, x4. So, these are the following combinations you have to find, and then you check which particular combination is again problem. So, then the management decision will be restricted to that particular difference only. So, as a result, since in this problem F is becoming significant, so it is the mandatory requirement that we like to check which two pairs are again which particular pair, or few pairs are statistically different. So, again for that we have to go for pairwise mean comparisons, and in this case we use actually there are many methods are there, but we have to follow this particular method to case kind of pairwise mean comparisons, and then we check which two pairs are statistically different as far as this particular problem is concerned. So, accordingly, so we have to move to check the pairwise comparisons, and here you see here corresponding to these 5 different situations. So, here these are all actually these are all called as mean of this particular series, and this mean of the individual series. Then we have a combined means, right. So, then we like to check actually whether the mean difference among these individuals are statistically different or not, but overall the problem is showing that they are statistically different. For instance, in this problem, so F is coming is 7.04, and we are actually we can reject this hypothesis on the basis of the kind of F criticals, and if fixing the kind of a critical value. So, we can see what should be the kind of decision which you have take and to know which two pairs are statistically different to each other. Okay. All right. So, this is the same things, and it is a kind of the kind of difference between two sample means and checking whether it is statistically significant or not. Okay. So, this is what the kind of so here we are actually to go for next level kind of inference, and in that case the typical structure of ANOVA is like this. So, having the sample information, so we are using the ANOVA, and then either you are rejecting H0 or not rejecting the H0. Okay. Do not reject H0 means actually you have to stop, the problem may come to end there, but if you are rejecting the true null hypothesis, then obviously the further issue will be starting, and either you create a confidence interval for these population means, and then we will check the pairwise mean comparisons. So, like previously, once you test, then accordingly you will see the confidence interval of this population mean or population mean difference, and then we will like to check whether the the pairs are obviously if F is coming significant means any particular pair, at least one particular pair will be statistically again different, and that particular pair will give you the typical management decision, what should be the next level kind of inference or the kind of strategy, right. So, accordingly we have to move, and then okay. So, first of all actually we can create a confidence interval, and corresponding to the previous problem, corresponding to this previous problem. So, okay. So, what will it do? Okay. So, this is what the problem. Okay. So, corresponding to this problem. So, now so the typical actually population interval will be, for these are all individual samples. Then as we have already discussed, for a particular population sample means, we can create a confidence interval, and having actually individual population mean sample means. So, you can go for population intervals, right, population intervals. So, for 89 the population interval will be like this, 75 the population interval. Of course, this is adjusted with the kind of t statistics, and because it is a pairwise mean comparison, and this is it, and the best statistic which you apply here is the t statistic, and this is how the t adjustment, and this is the sample specific, because we have a different sample size, and accordingly we have a different population interval for different means, right. So, for a particular means, the confidence interval is different, again for different means. So, the confidence interval will be again actually different. So, likewise actually we have actually different kind of structure, and this is the mean, and this is what the confidence interval for populations, right. So, corresponding to this, so we have to check actually the kind of significant difference, and by using Tukey's pairwise comparisons. So, this is what the actually the test statistic which you have to calculate, and that is depends upon your sample size and mean square MSE, and that is actually within group, and then it will compare with individual test statistics. So, in the next slide I will give you the kind of exposure through which you have to take a kind of require. So, the null hypothesis will be the first the typical comparison will be like this, and again we have 6 different cases to test depending upon the particular case situations, right. Since we have actually 4 samples with 2 pairs, then we have to go for 4C2. If there are 5 different cases, then you will go for 5C2 pairs, right. So, accordingly in this problem, so we will check how many cases we can actually test, right. So, you see here corresponding to this 5 samples, corresponding 5 samples, sample 1, sample 2, sample 3, sample 4, sample 5, and this is what actually combined t statistics, and that is the benchmark through which you have to check whether there is a significant difference. There typically actually this is called as post hoc analysis, right. So, now the first case will be mu1 mu2, then mu1 mu3 mu1 mu4 mu1 mu5, similarly mu2 mu3 mu2 mu4 mu2 mu5, then mu3 mu4 mu3 mu5 and mu4 mu5. Okay. So, these are possible cases with 5 different samples, and mu1 mu2 equal to they are equal, population mean are equal, and with the help of sample means. So, here the sample means, and with the sample means difference, and that is with respect to the benchmark to case t statistics. So, we will see actually whether this difference is actually overtaking the kind of critical value. So, in this case it is 14, and so it is coming actually 13.7. So, that means it is overtaking. So, it is statistically different, and again this is also statistically different. This is not statistically different, because this value is lesser to the critical value. This is again not statistically different. This is also not statistically different, and this is again statistically different. So, this is not this is again statistically different. This is not, this is not. So, that means out of 10 different cases. So, 1, 2, 3, 4. So, out of 10 cases, so 4 different cases we will find significant difference, that is with respect to sample 1, sample 2, sample 1, sample 3, and then sample 2, sample 4, and finally sample 3 and sample 4. In other case there is no significant difference. So, that means, so the management problem will be restricted to these samples now again. So, we have to check where is the kind of difference and how is this particular difference. So, the management problems accordingly or the management decision need to be taken care again as per the particular requirement. Okay. So, this is how the typical actually graphical structuring regarding the difference between the two different pairwise comparisons. So, with the help of 5 different situations earlier. So, 3 situations or 3 different occasions we are actually finding the difference are statistically different, and other cases they are not statistically different. And so, where it is not statistically different, so the problem will not be so serious, but where there is a statistical difference, then the inference will be different, and accordingly take into considerations and will analyze the problem as per the kind of management requirement. And this is another kind of comparisons. You can go to the Excel sheet and then you will do some kind of comparative statistics, and then you see first you go for the kind of combined a kind of test, that is through F statistics, and if F is coming statistically significant, then you have to see which particular pairs are actually reflecting. If F is not coming significant, then the next level search or next level inference is not required. But if F is coming statistically significant, that means the situation where F calculated will overtake the critical, then you will find which pairs are again coming into the pictures for that means statistically different, and then you have to think how it can be actually materialized as per the kind of management need or management requirement. Okay. So, this is what actually the kind of these are all again advanced level of kind of things like models, factors, and designs, typical design of experiments. So, that means the so far as scope of ANOVA is concerned, it has it has a kind of multiple impact or multiple use, or having enough scope for integrating with the different problems, and the same structure can be extended with 2A ANOVA, 3A ANOVA, and kind of MANOVA, right. So, in the meantime we will stop here, and in the next lectures we will extend this ANOVA with 2A contest and 3A contest, and we will check what is the kind of structure and the kind of outcome, and what should be the kind of typical management decision corresponding to multivariate case, and that too in the case of 2A ANOVA, 3A ANOVA, and MANOVA. With this we will stop here. Thank you very much. Have a nice day.